So I would like to say something about, introduce the Wasserstein gradient and also the Wasserstein second gradient. But before that, let me start with something we are more familiar with. Gradient. Recall that H is the Hilbert space L2 of 0, 1, RD. And reminder, let U hat be a function from H to R. We say that U hat is differentiable at S in H with gradient zeta in H if the following hold: U hat of Y equal to U hat of X plus Y minus X zeta, the inner product in the H norm, plus little o of Y minus X in the H norm. And if instead we do this, we are going to say in the subdifferential. And if we do that, we are going to say it, we are in the superdifferential. Okay. So I am going to look at two random variables, and I would like to define an equivalence relation between them. So given X from 0, 1 to RD, I have Lebesgue measure here on X, and I am going to use that to define a measure mu on RD. So by definition, mu is the push forward of, so here, let me put anything nu naught, and let me put anything here which is RD, so that I don't need to repeat the definition in the general case. So I am given this, I am given that. And now definition. Mu is a push forward of nu naught by X is a measure on RD defined as mu of a set B is nu naught of the set of X in RD such that S of X are in B. In other words, it is nu naught of S inverse of B. So what I done here is I have RD, and then I have RD. I have a measure here, nu naught, and I have a map, X. So every time you give me a set B, I am going to look at the pre-image. And I am going to measure the pre-image with a mu naught, and I will say that this is the measure of B. So this gives me a way to define an equivalence relation. Let X and Y be in H. Then S is equivalent to Y, means that if I push forward the Lebesgue measure on 0, 1 using S, I get the same thing as if I push forward the Lebesgue measure using Y.
So these are maps from 0, 1, and 3. X and Y have to be, but these are L2.
Yes, this is L2 of 0, 1,
Okay.
RD. What?
And it's true for one set or for all subsets, or what are we talking about?
Here, for all sets, for all B, subset of RD.
So forgive me, but this is typically what happens in Lagrange coordinates.
Oh, please go to RD.
For instance, here it will be what? Yes. What was the question? Yeah.
I know this is simple. So X and Y are functions on 0, 1, L2 functions in the RD.
Yes.
So they push the big measure on RD. Okay.
So they push the Lebesgue measure
They push
to
RD. So
to RD.
all right. So X and Y are only to find out. All right. Yes. Okay.
So for example,
So big P is 1 and little p is. So 0, 1 could be 0, 1 could be
I could replace that by any set which is non-atomic. Yes. So I choose 0, 1 as my Lagrangian coordinates. So I am going to define. So in fact, 0, 1 may look mysterious. What the probabilists do, the definition I am going to give, the probabilists, they put any set omega here. And they require that a measure which has no atom.
But you're never going to use the ordering of 0, 1?
Yes, I am not going to use the ordering, but it was very convenient when I wanted to show that RD cross RD was a subset of the Lebesgue space. If I was in the square, then I was going to divide into small square in order. And on 0, 1, I didn't need to think about how I do it. Say it again.
They could be just different orderings of the same.
Exactly. Exactly.
That's the motivation.
Yes.
So you don't care about the labels.
Exactly. Yes.
So you lost the big measure out there.
You said no?
Measure Newsom 0.
Yes.
Is the big measure on 0, 1.
Yes. So here, I will be saying that the Lebesgue measure of S minus 1 of B is the Lebesgue measure of Y minus 1 of B for every B. Exactly. Yes.
It's just saying there's the same number of particles in B, in X and Y.
Yes.
That's it.
Yes.
Yeah, okay.
So I am going to denote the class of equivalence of X by this. So as I did before for the set of permutation, I want to define a metric. The distance square between X and Y is the infimum over S prime, Y prime in H. The norm between X prime minus Y prime square, the H norm, where I impose that X prime is in the class of equivalence of X, and Y prime is in the class of equivalence of Y. And so set mu to be the measure X, push forward the one-dimensional Lebesgue measure, and nu equal to Y, push forward the one-dimensional Lebesgue measure. Then it has been known for a long time that the distance square, the distance between the class of equivalence of S and the class of equivalence of Y is the Wasserstein distance between mu and mu. So here you have two options. If you don't know what the Wasserstein distance is, take this as a definition. If you know what it is, take this as a theorem. So now that I have this, let us compare Eulerian and Lagrangian coordinates. So assume I have T goes to ST, the trajectory of a particle. Then S dot T is the velocity in Lagrangian coordinates, and call V at time t the velocity in Eulerian coordinate. Then the relation between V and S dot is S dot T equal to Vt of St. So I want to write that to say that St of any omega is in Rd. So where Rd, where omega is in 0, 1. So the domain of V is a subset of Rd, whereas the domain of St is a subset of 0, 1. Therefore, when I go from Eulerian to Lagrangian coordinate, when I'm working with vector field, which are defined here in Lagrangian coordinate, I'll look for vector field, which are defined here on Eulerian coordinate. So this is what we are going to do for the gradient back to the gradient. Which is the Hilbert gradient of u hat at x. So this is in the Hilbert space H. Therefore, it is defined from 0, 1 into Rd. If I want to associate a vector which will be defined from Rd to Rd, because I want to go from Lagrangian to Eulerian coordinates. I am going to make two assumptions. I am going to assume u hat of x equal to u hat of y if x are equivalent to y. In other words, I am saying that u hat is in fact defined on the quotient space. And when this happens, I will say u hat is a rearrangement invariant. Now, there is a definition of define set u of mu to be u hat of x, where mu is a push forward of the Lebesgue measure on 0, 1. I want to define the gradient of what the gradient of u at mu will be. And I will start with something which is very imprecise first because it helps. I just want to explain the definition. And then later we can try to do something more rigorous. So this relation, if this represents zeta, I want to define a gradient which I am going to call psi. And the relation between psi and zeta will be zeta equal to psi composition of x. So definition. A vector field psi from Rd to Rd is in the gradient of u at mu if this hold, if this equality hold, if for zeta equal by definition psi composition x, this equality hold u hat of y equal to u hat of x plus y minus x zeta, so psi composition x num plus little o of y minus x, the h num, for all x, for all y, such that the distance between y and x in the H1 norm is the distance between the class of equivalence. So I want to choose a y such that this minimum is achieved. And only for that I have a Taylor expansion. So I need to make two corrections to make this definition rigorous. It is very vague to say a vector field. I need to tell you.
But how does this depend on x? For bracket x?
How it depends on x? So, the distribution of S is mu. So if for S and S push forward L1, 0, 1 equal to mu.
So this is 4x.
Yes.
Each x has its own.
Yes. So I want to specify two things. This is too restrictive. I need to replace x by an element of its class of equivalence there, and there by an element of its class of equivalence, because otherwise I may have an empty set.
Yes.
And so I need to correct this. I need to correct this. So I will say there exists, if there exists S naught, if there exists H, such that this hold, and that hold for every Y such that this equality hold. So this will be the correct definition.
It depends on the equivalence class.
Yes, it depends on the equivalence class. So here is something else. Yeah. I postpone that as much as possible because it is not necessarily intuitive for everybody. So first, I said unadmissible because I can show you that when I have one, I can construct many over one. Mm-hmm. So I claim that whenever this is a well-known fact, if I take a W, divergence of W by mu equal to 0, then psi plus W also satisfy the condition. However, among those satisfying this condition, I can look for the one which minimizes the L2 norm of psi. There is a unique one. Is unique. And so when I say talk about the gradient, I mean the one with the minimal norm.
This is related to incompressible fluid now.
Yes.
Precisely.
Yes. Now I need to specify, I still did not tell you in which set I am minimizing. I need to specify that. you can take L2 RD to RD with respect to the measure mu. But you can check that even if you take that, the minimum will be attained in the following set. So this is a set of vector field. It will be very nice if the vector field was of class C infinity. But this set is too big for us to expect that to be true. What is true is that you close this in the L2 norm. So you can check that even if you start with a psi here, the minimum is always in this set. And this is defined by Ambrosio, Gigli, and Savary. Gigli and Savary. They call this the tangent space to the Wasserstein space at mu. And they gave many other justifications why this is the good concept of tangent space. They show that if you take any trajectory, then the tangent vector to the trajectory, you can always find one which is in this space and it has a minimal norm. So one can show that this definition, call this definition 2. Definition 2 is equivalent to Ambrosio, Gigli, and Savary definition. And if you don't know Ambrosio, Gigli, and Savary definition, take this as a definition of Ambrosio, Gigli, and Savary. Okay, so to show a relation between, so in fact, this is a theorem which is due to myself and Tudorescu in 2019. And you can show that U is differentiable at x if and only if it is differentiable at any other s prime which is equivalent to x. Okay, so let me summarize what we have gotten. The gradient, Hilbert gradient of u hat at x equal to the Wasserstein gradient of u at mu, composition x, if x push forward the one-dimensional Lebesgue measure to mu. And what is hidden here is I am saying this differential exists if and only if that differential exists. And this result is true about a subdifferential. If I replace differential by subdifferential, then this factorization also holds. So the first time when this result, what motivated us to study this identity was Pierre-Louis Léon assume if u hat is continuously differentiable near x naught, near x, then you can factor, you can have this factorization. So this requirement, when you are studying viscosity solution, this is a too big of requirement. When you are solving viscosity solution, you want to know if the subdifferential at a specific point is empty or the superdifferential is non-empty, and you don't have the information that something will happen in the neighborhood of a point. Now, if you give up this condition of continuously differentiability, then it makes the proof of this result much harder.
Subdifferentiability mean that you're allowing characteristics intersect or something like that? Is that buried in there somewhere? I mean, viscosity solutions are geared towards, discontinuous derivatives. So something like that
Yes, subdifferentiability will allow several paths to go through.
Okay.
Okay, now I recall what the definition of subdifferential or a differential is. Let me recall what a Hessian is of u hat at x. So a bilinear form dx from H cross H to R is the Hessian of u hat at x if you can have a second order expansion. And so I am skipping some assumption. So I should say, assume u is defined in the neighborhood of S. Assume we know that it is differentiable in the neighborhood of X. Then I can define the Hessian the following way. If u hat of y equal to u hat of x plus the gradient of u hat at x, y minus x, plus 1/2 bx, y minus x, y minus x, plus little o of y minus x squared h. And by analogy, as before, if u hat is rearrangement invariant and u of mu is defined to be u of x, u hat of x, where x push forward the Lebesgue measure to mu, then u hat is u is twice differentiable if you can write this expansion under the same constraint. Then you have a relation, the Hessian of u hat at mu. If you apply it to psi compose x, psi compose x, so no, I should multiplied at x, psi, that was correct, psi compose x, psi compose x. This will be regression of u at mu applied to psi. So again, I didn't define regression, but you repeat this same definition with this constraint, and that gives you the definition of regression. And once you have that definition, you have this theorem. So let us do an argument by induction. We'll do it for the third derivative, fourth derivative, and so on. So this is a way you can prove that 0 is of class C infinity, because of the following. You prove nice property. I want to make a statement. I want to state a theorem. Theorem. Assume U has a special form. Assume U hat of x is the integral from 0, 1, phi of s of omega, d omega, and assume that phi is of class C3 of and bounded. So let's say of compact support, RD. And I look at that particular function. Then I say that if the function u hat is of class C3, then it is analytical. So I can spend a good time trying to prove that result. But in fact, what I'm going to prove is if this is true, phi is 0. So here is my statement. Assume this is true. If u hat is of class C3, then phi is a polynomial of degree at least, at most 2. And so if the function is of compact support, then it has to be 0. So the point I am trying to make here is there is something mysterious here. The second order regularity in Wasserstein space corresponds to the second order regularity in the Hilbert space. But when you go over the second order, then there is no correspondence. So let me try to give you an idea of the proof here. Assume u hat is 3 times differentiable. So everywhere, right? Because I said on H, everywhere. Then I am going to compute the derivative, the restriction of the derivative on the Dirac masses. And I know how to do that. So I claim that I'll have a trilinear form, psi, psi, psi. This is in L2. That is in L2. And this is in L2. And I'll write it in terms of derivative of psi, third order derivative of psi, psi I, psi j, psi k. So the only way this can be, so this is in L2, that is in L2, this is in L2. The only way this can be in L1 is that is 0. Now, if you want to write a rigorous proof, right? I mean, once you have this intuition, then you take a Dirac mass and you modify with a Gaussian. And you write the Taylor expansion, and you let the parameter in the Gaussian go to 0, and you start making terms disappear, and you end up with an expression like this, where if this is not 0, then your expression will go to infinity. And so you prove that the third order derivative must be 0. However, you can continue as a Wasserstein function. The third order derivative of this exists for any phi. And so the invariance property on the Hilbert space put a bigger restriction. So I was saying at the beginning, it is very convenient to work on the Hilbert space because it is a flat space. But you can do that when you are dealing with first a second order equation. When you go with higher order equation, when you need higher order derivative, then you'll have to give up the Hilbert setting and work purely on the Wasserstein setting. So once we have all this definition, the question is, can we compute? I give you a function on the Wasserstein space. I ask you, can you compute the gradient of this function? Can you compute the Hessian of the function? And let me give you, I am going to give you some intuition. What I am writing is not always correct, but this is a way to think when you are computing the gradient. So assume I am given a function u from the set of probability measure on Rd to R. And let mu Rd. I am going to look at if the limit when epsilon goes to 0 of u of 1 minus epsilon mu plus epsilon mu prime minus u of mu, if the limit exists, and if I can say that I have a representation formula for that Rd delta L2 delta mu of mu q mu prime minus mu dq. Okay, so I give you a function u on the set of probability measure. Identify the set of probability measure with the L1 function which has a density. Being on the set of such that the integral of the density is 1. This is a too small set. I leave it. I extend my function to the whole L1. So I don't impose any more than the density. The integral of the density is 1. Assume that I am lucky when I do my extension. I get a function which is differentiable in L2. Then here, this is the definition of L2 differentiable on a Hilbert space. However, here, I am not requiring all of these extra assumptions I made. I am not requiring that I have an extension which has a nice property and I am dealing with which are measured with respect to absolutely continuous function. I am writing this formula, and I want to draw your attention that I cannot call this an L2 differential because what is here is not necessarily in L2. So you can see that since mu and mu prime and mu are probability measure, if I find any function which satisfies this property, if I add a constant to it, the function plus a constant will satisfy the property. I can uniquely determine this by imposing that the integral over Rd delta u over delta mu q mu dq equal to 0. So once you do that, you can show that if such a representation formula exists, then this function is uniquely determined. Okay, so that is concrete. For instance, example. Assume I take u of mu is the integral over Rd of phi q mu dq, then du over d mu at q mu will be phi of q, but the average of this may not be 0, so I have to subtract by that to make sure the average is 0. Okay, so if instead of this I give you 2 u of mu equal to 1/2 the integral of phi convolution mu q mu dq. Likewise, you can compute the first variation and show that the first variation is this convolution minus an appropriate constant, which is going to make it equal to 0. So on the smoothness assumption, and this can be found in the bigger lecture note by Cardialagate. Larry Lasserie and Lyon. If delta u over delta mu exists and is of class C1, then the Wasserstein gradient of u at mu applied to q is the classical gradient of the L2 q mu. So this result is going to help a lot when you are computing and you want to predict what is correct, what is not correct. This is going to help a lot. But in general, if I give you the gradient, the Wasserstein gradient, it is not the gradient of a function. According to the definition we wrote, it will be, you will take a limit of such objects, and the limit in the L2 mu norm, and you will end up with something which is not necessarily a gradient. And you can construct example where you don't have enough smoothness to have such a nice property. So we know how to compute the gradient in the smooth case. Let me tell you what is the Hessian in the very smooth case. theorem. Assume U is twice differentiable. Plus some technical condition. So the technical condition will say, for instance, this is continuously differentiable, the second variation exists, and so on. But assume it is twice differentiable so that the expression I am going to write next makes sense. Let mu be in a probability measure, and let psi be a vector field. So let us say psi is the gradient of a function. The function is of class C infinity. Okay, so I take a special vector field, and I want to write the Hessian. Then the Hessian of U at mu, if I apply to psi, this will be the integral over Rd. I am going to take the divergence with respect to Q, the Wasserstein gradient of U, Q mu, integrate that mu to not the divergence. Psi of Q psi transpose of Q mu dq plus the integral over Rd cross Rd psi transpose of Q prime twice the Wasserstein gradient of U at Q prime mu psi of Q mu dq prime. Okay, so I am telling you that I have a representation formula for functions which are twice differentiable on the Wasserstein space, or equivalently, I am telling you that if I have a function on the Hilbert space, L2 of 0, 1, if it is rearrangement invariant, then I have a representation formula for the Hessian of that function. So, yes?
What's that second, that gradient mu?
So I take the gradient. Gradient mu is the Wasserstein gradient.
Yeah.
And I differentiate a second time. I take the gradient of the gradient.
Oh, the Wasserstein gradient.
Twice, yes.
I see. Okay, so this I see is very special. So, because if you did the first derivative applied to C, it's just the integral of Z dotted with that, which is sort of a natural chain rule.
Yes.
So you get these sort of extra.
Yes. So you can show that this extra thing is you compute the second derivative respect to mu at Q prime mu, and then you take the gradient with respect to Q prime, the gradient with respect to Q. You can, right? Because once I know what the Wasserstein gradient is, if I want to compute the gradient of this, I am going to apply the variation and the gradient. And then I need to check that it commutes. Yes. I will say that in the case of Benamou-Brenier, since this will be the velocity, then the velocity will be the gradient of a function. And this function will satisfy your Hamilton-Jacobi equation. So I am slowing down because I am concerned. Now I am concerned that maybe if I do something complicated, you say, that's it. I won't listen to him again. Okay, so.
So the first one, speaking of Benamou-Brenier, so the first one, there is a chain rule that if I take a path,
Yes.
take a derivative,
Yes.
then that gradient dotted with the vector
Yes.
field. If you take two derivatives,
Yes.
is there?
Yes.
Okay.
Yes.
So it is kind of consistent with
Yes.
normal calculus.
Yes. Okay, so let us change a little bit, and then we'll come back to this. So I want to define some stochastic paths on the set of probability measure. So let me start a setup. I am going to choose WT, standard Brownian motion, starting at 0. Okay, so this means that I assume I'm given omega p, a probability space. And W is in fact defined on 0 plus infinity cross omega into RD. So this is the d-dimensional Brownian motion. And again, I've been doing that often. When I write a WT, it means this. So given a measure, mu, on the set of probability measure of RD, I am going to define identity plus square root of 2 epsilon WT, and I will push forward mu. And I'll call this B mu T. So I want to view this as a Brownian motion, but I will not call on the persistent space, but I will not call it a Brownian motion. So note that this is a stochastic path, because for each W fixed, I have a measure which depends on W. So let me define this measure differently. So the measure, if you take a B, T mu, of a set A, if A is a subset of RD, you are just taking mu of A and the translation by square root of 2 epsilon W T. So if you think about what this is doing, assume that mu is an average of Dirac masses. Then B T mu is 1 over n, the sum delta Si plus square root of 2 epsilon W T. And so you see that this is what corresponds to the common noise, because everybody is moving randomly, but in the same random way. So let me put a beta here, because I will forget and confuse myself. For epsilon greater than 0, so and beta greater than 0, I am going to consider the kernel of the heat equation, exponential of negative z squared divided by 4 t epsilon divided by the square root of 4 t epsilon pi 4 pi to the d. Okay, so if you apply that to a measure, then this measure satisfies the heat equation. So I am going to do this. Given mu on the set of probability measure on RD, I am going to do G T epsilon convolution mu. And so I have a solution to the heat equation. So what this is doing is, if you look at it in terms of independent noise, if you take n particle, the particles are moving with independent Brownian motion. And what I am going to do, I am going to apply identity square root of 2 beta Wt. I am going to push forward this. And so I will get something which depends on epsilon, beta, mu, and it is a time-dependent path. And I want to tell you that this satisfies a heat equation on the versus time space. So if I put epsilon equal to 0, it will satisfy a heat equation where this is a partial Laplacian. So here is what I want to do. You will be very tempted to given U0 from the set of probability measure on RD to R, you will be very tempted to define U0 of sigma t epsilon beta and take mu. And you take the expectation. And you call this U of T mu. So you'll be very tempted to say, what is the equation satisfied by this mu? Okay. So one test, first you say, let us take mu to be an average of Dirac masses. And you can write explicitly what U is, and you can see explicitly the equation is satisfied. So let me let me say example. Let me assume that epsilon is 0. And let me assume that d is 1. And define u of t s1 sn to be capital U of t 1 over n sum I from 1 to n delta Si. So of course, if I want to see what equation this satisfies for every mu, I want to understand when I have Dirac masses, what is the equation it satisfies. So one can check that dtu equal to the sum over ij, the partial derivative with respect to Si, the partial derivative with respect to Sj of little u. So if you look at in terms of Fourier transform, what corresponds to this is the sum of psi I square. Sorry. It is the sum of psi I, psi j. So this is negative pi, negative 4 pi square. This is non-negative, but it can be 0. And so this produces an elliptic operator which is degenerate. So you see that this operator will not give you smoothness. It is hopeless to think that you have smoothness. So we have just observed that, sorry, there is a beta in front of it. We have just observed that if I only have common noise, there is no way I am going to improve smoothness over time. And in fact, I hope to write to you a harmonic function. And I am going to write a harmonic function which is of class C2, but cannot be of better class than C2. Now, if I add epsilon greater than 0, this is going to add epsilon sum d si square u. And you see that immediately for epsilon greater than 0, I get a uniformly elliptic operator. And so this is going to improve regularity in some direction. When I say some direction, remember that here, I will not be able to reach all direction in the Hilbert space. I will be able to reach only spatial direction. Now, let me define what I am going to call the partial Laplacian. The tangent space T mu of P2 of Rd, I can take the space spanned by the constant vector. So take any orthonormal basis and add to it its orthogonal. I am going to define the trace of this restricted to that space. So the partial Wasserstein Laplacian of u at mu will be the sum I from 1 to n, the Hessian of u at mu applied to ei. And of course, you can check that this definition is independent of the orthogonal basis I take. If I want to have an operator which is going to improve smoothness, you see this operator is telling me something only in a spatial direction. If I want an operator which is going to improve smoothness, I need an operator which takes into account all the direction. And not only that, I needed to care about this part, which is degenerate, and add something which is non-degenerate. So call this H1. I am going to define O, U of mu to be the trace sum I from 1 to D, H1 of E1, E1. So this is the common noise, and this is the individual noise. So now let me state a theorem about this. If I define U to be that theorem, the partial derivative of U with respect to time is epsilon O of U plus beta versus Laplacian of U. So to prove this, you just need to check Ito formula. So once you check Ito formula is satisfied, you get the proof of it. So how do you check Ito formula? You want to write for an arbitrary V, you want to write VR sigma T epsilon beta R minus Vs sigma S epsilon beta equal to something, integral from S to T, and so on. Again, you assume that your mu is a Dirac mass, average of Dirac mass. When your mu is average of Dirac mass, then you are back to the finite dimensional case, which we'll know that well, and you write Ito formula there. And then you let n go to infinity. It is enough that I assume that V is continuous to pass to the limit, and so you get this for general measure. So it needs some technical thing to make sure you have a good convergence, but these are not difficult to check. How much time?
It's up to you.
Okay.
No more than 10 minutes.
Okay. I lended you 9 minutes. This one?
The OU is smoothing by itself?
Yes. Yes. So it is moving. I can give you a class of function where it has a smoothing effect. So before that, let me make a remark. Take U of mu to be the integral over Rd cross Rd of phi of Q minus Q prime mu dq mu dq prime. Then this is the harmonic function. Yes, you just compute. So you remember I told you how to compute the gradient of this, and then once you have a gradient, you compute the second gradient, and you replace in the formula, and then you see that it is harmonic function, which shows that you cannot improve regularity. Because if I start with a C2 function, and I solve a CT equation, I get a constant function, the regularity doesn't change. Now, interesting class. I am going to look at u of mu of the form the integral over Rd cross Rd n time phi of x1 Sn mu ds1 mu this Sn. So for this class of function, or finite combination, or infinite combination, so if you take infinite combination of this class of function, you can show that this operator by itself improves regularity. So I am going to put some coefficient. It is like when you do the Fourier decomposition. You do a Fourier decomposition with some coefficient, and you see that this is going to help you. You can write explicitly a formula where this is going to help you improve the regularity. So to see that, let me describe some of the eigen function. Given psi 1, psi n, define phi of psi 1, s1, sn, to be the exponential of negative 2 pi I, psi 1, s1, plus psi n, sn, and then define u as above. Then direct computation lemma. You can check that negative u equal to lambda square u, where lambda square is the sum psi I square I from 1 to n. And negative O of u equal to lambda tilde square of u, where lambda tilde square is the sum I from 1 to n psi I square. And so if I take a combination, the integral ak of psi exponential of negative 2 pi I psi 1 s1 psi k sk mu ds1 mu dsk. If I want to check the heat equation which is satisfied by that, you can write explicitly the solution. You can write a representation formula using this eigenvalue, and it tells you how you improve regularity, why you improve regularity when you add this to the Laplacian operator. Okay, so to conclude, I would like to say this second part of my talk, I made a presentation on the partial Laplacian and this operator. So this is a common noise operator, the individual noise operator. And then at the beginning of my talk, I insisted more on the Hamiltonian and the Lagrangian. So what Minfield Game is interested in, in combining the three mechanisms together. So the evolution will be governed by the Lagrangian. It will be governed by the parameter in front of the common noise and the parameter in front of the individual noise. And without the presence of this. It doesn't matter what beta is. It doesn't matter what beta is. So beta is the coefficient in front of that, and epsilon is the coefficient in front of that. If you don't take epsilon greater than 0, there is almost no result. I mean, the result you get in the infield game are very limited. I'm going to stop here.
Okay, thank you very much.